हाँ, कृणाल चालू करिए।
Right. So,
नमस्कार।
very good. Namaskar, sir. A very good morning to all. It's my great pleasure to introduce Mr. Ram Chouksey, sir. So, he is working as a scientist F and nominated record officer at Solid
नमस्कार।
State Physics Lab, DRDO, Delhi. He is pursuing his PhD in management from ABB IIM, Gwalior, Madhya Pradesh. Apart from this, he has several awards in his bag. He has got a first position in National Productivity Week in 2000. He has got a Technology Group Award for CZT Technology in 2008. He has been achieved with the Agni Award for Self-Reliant in Crystal Growth Technology in 2015. He has been also achieved with Lok Vigyan Alankaran by Gunjan Kala Sadan, Madhya Pradesh in 2019. He has achieved the commendation certificate for the record management in the year 2020. Again, he has been awarded with the Agni Award for acoustic emission project management in 2023. So, on behalf of MM-TTC IDVB Jabalpur, I welcome Mr. Ram Chouksey sir and request him to kindly deliver his lecture. Thank you, sir.
Respected Pandey sir, Chandok sir, इस व्याख्यान के लिए आपके द्वारा आमंत्रित करने का लिए मैं आपका आभार व्यक्त करता हूं। मैं आज आपको डीआरडीओ में जो शोध कार्य चल रहे हैं उनके बारे में चर्चा करूंगा। सामान्यतः मैं अपने शोध कार्य के बारे में इसमें आपको बताऊंगा। मैं आईआर डिवीजन में कार्य किया हूं, तो सॉलिड स्टेट फिजिक्स से रानी दुर्गावती विश्वविद्यालय से स्पेशलाइजेशन करने के पश्चात मुझे यहाँ आईआर डिवीजन में कार्य करने का सौभाग्य प्राप्त हुआ, जिसमें क्रिस्टल ग्रोथ की जो हमारे प्राध्यापकों के द्वारा पढ़ाई गई तकनीकी थी, उसमें मैंने यहाँ कुछ सुधार करके शोध कार्य किया। सामान्यतः हमारे क्रिस्टल ग्रोथ विभाग में कैडमियम जिंक टेलुराइड, गैलियम आर्सेनाइड और जर्मेनियम क्रिस्टल के ग्रोथ की तकनीकी का विकास किया गया। हम जो थ्योरी पढ़ते हैं और जो प्रैक्टिकल करते हैं उसमें जमीन आसमान का अंतर रहता है। तो 2,6 और 3,5 कंपाउंड सेमीकंडक्टर के क्रिस्टल ग्रोथ, एपिटेक्सियल लेयर ग्रोथ और डिवाइस फैब्रिकेशन का कार्य सॉलिड स्टेट फिजिक्स लेबोरेटरी में किया जाता है। यहाँ पर सॉलिड स्टेट डिवाइसेस बनते हैं। तो सबस्ट्रेट मटेरियल पे मेरा कार्य रहा है। सबसे पहले मैं कैडमियम जिंक टेलुराइड क्रिस्टल के बारे में आपको बताता हूँ। फोकल प्लेन एरे नाइट ड्रिवन डिवाइसेस में ये यूज होता है। इसके निर्माण के लिए हमें एक आधार परत की जरूरत होती है, तो कैडमियम जिंक टेलुराइड को सिलेक्ट किया गया क्योंकि इसका एपिटेक्सियल ग्रोथ में एप्लीकेशन है, डिवाइस में ये यूज होता है और आईआर ऑप्टिक्स में ये यूज होता है। इसकी जो प्रॉपर्टीज हैं, ट्रांसमिशन, इलेक्ट्रिकल और फिजिकल प्रॉपर्टी के कारण हम इसको सेमीकंडक्टर टेक्नोलॉजी में ग्रोथ के लिए यूज करते हैं। जनरली क्रिस्टल ग्रोथ की जो टेक्नोलॉजी हमने पढ़ी है वो मेल्ट से ग्रोथ, सॉल्यूशन से ग्रोथ, वेपर ग्रोथ फ्रॉम वेपर से हैं। इनकी डिफरेंट टेक्निक्स हमें पढ़ाई जाती हैं। तो कैडमियम जिंक टेलुराइड को ब्रिजमैन टेक्निक से ही ग्रोथ के लिए चुना गया, क्योंकि यहाँ पर ब्रिजमैन टेक्निक में यूनिडायरेक्शनल फ्रीजिंग होता है और ग्रेन साइज हमको सबसे ज़्यादा मिलता है। बहुत सारे मटेरियल्स की यहाँ पे ग्रोथ होती है डिफरेंट यूज के हिसाब से। जोन मेल्टिंग है, ट्रेवलिंग हीटर मेथड है, चक्रॉल्स की मेथड है, जो जर्मेनियम क्रिस्टल है और गैलियम आर्सेनाइड क्रिस्टल है, उनको चक्रोल्स्की मेथड से ग्रो करते हैं। ये डिपेंड करता है क्रिस्टल ग्रोथ के प्रॉपर्टीज और ग्रेन साइज के ऊपर। इसके पश्चात सॉल्यूशन ग्रोथ की, जो कि एपिटेक्सियल लेयर ग्रो की जाती है, वो स्लाइडर, टिपिंग और डिपिंग मेथड से ग्रो किया जाता है। ग्रोथ टेक्निक का जो सिलेक्शन किया जाता है वो क्रिस्टलाइन परफेक्शन और इम्प्यूरिटीज को लेकर के होता है। सो गुड क्वालिटी क्रिस्टल ग्रो करना हमारा एम रहता है विथ कंट्रोलिंग ऑफ इम्परफेक्शन एंड इम्प्यूरिटीज। सो जो ब्रिजमैन टेक्निक है उसको कैडमियम जिंक टोलुलाइट के लिए सुटेबल पाया गया। जो कैडमियम जिंक टोलुलाइट क्रिस्टल है वो फोकल प्लेन एरे में एक डिटेक्टर डिवाइस के रूप में कार्य करता है। उससे नीचे अगर हम देखते हैं तो उसमें एमसीटी एपिटेक्सियल लेयर होती है और सबस्ट्रेट के रूप में सीजेटी को यूज किया जाता है। एमसीटी मरकरी कैडमियम टोलुलाइट जो सबस्ट्रेट रहती है उसका वो ट्रांसपेरेंट रहती है आईआर रीजन में। और एपिटेक्सी के लिए जो सबस्ट्रेट रिक्वायर्ड होती है वो कंपैटिबल होना चाहिए ऑप्टिकली, केमिकली, स्ट्रक्चरली एंड मैकेनिकली मैच विथ एमसीटी। दीज आर द properties of different substrate material for required for the focal plane array and IR detectors. Here earlier we are using silicon and gallium arsenide and cadmium telluride. Now we are using cadmium zinc telluride with zinc 4% addition because it's harden the substrate material, because cadmium telluride substrate are brittle, so in use they are by mechanical stress they are broken. Advantage over cadmium zinc telluride over cadmium telluride is the because latest mismatch is 0.3%, chemical and physical compatible, and it is transparent in IR region. The problem associated with cadmium telluride substrate is low thermal conductivity, low stacking fault energy, low critical resolved shear stress, and reproducibility is the main issue. And large diameter is of single crystal or large grain size is the main impediment of the growth technique. Now, nowadays, cadmium zinc telluride emerged as a potential candidate for the substrate material. Here, zinc is with 4% is suitable for MCT epitaxy layer growth, and this gives us better crystalline quality with low defect damage. And zinc segregation is resolved with annealing, uniformly distribution with annealing of in situ annealing of the crystal during the growth process. These are the some parameters of the cadmium telluride, gallium arsenide, and silicon crystal. Now, these are the advantage of growth from melt. Contamination of the crystal with solvent is not a problem, and large growth rate are also possible. Large size crystal can be prepared with this technique, and other techniques are the liquid encapsulated Chakrolsky method, traveling heater method, and solid state recrystallization method. And in Bridgman method, two methods are there: horizontal Bridgman and vertical Bridgman. Here for large area grain or single crystal purpose, we are using vertical Bridgman method as a unidirectional freezing method. Other method for CJT, LEC, traveling heater method, and SSR method, crystalline quality is not good. Crystal ingot diameter is less. And if Chakrolsky method, the boron contamination is very high, and growth rate is very slow, and tellurium precipitate is there. And horizontal Bridgman method half the yield because of the diameter of the crystal. Advantage of vertical Bridgman is the faster growth rate and larger size crystals and better crystalline quality. This is the phase diagram of the crystal growth technique where thermodynamics study is required. This is the theoretical phase diagram of the pseudo-binary section of the liquids or solids for the cadmium zinc chloride and zinc telluride system. This is the post-solidification cooling pattern. By these three theoretical things, we are optimize our parameters, and with these things we grow the crystal. This is the required thermal profile of the furnace, and from constant zone to gradient zone we are moving from top to bottom. Limitation of this technique, because problem of furnace design and temperature control is very critical. It is often difficult to find a suitable material which will be contain molten material at elevated temperature without contamination. And design of the growth process, the material property, and with temperature technique requirement. Considering all these factors, CZT growth process and fabrication of a substrate designed and optimized. The procedure of the is very lengthy for this crystal growth. Synthesis of polycharge, we are using cadmium, zinc, tellurium, 7N pure cadmium, zinc and tellurium, and select method is Bridgman method. After crystal growth, identification of 111 plane and orientation cutting along 11 plane. We are using X-ray goniometer for plane identification. Then shaping of substrate by required size. Earlier we are using 15 by 15 and now 25 by 25 required for device application. And substrate preparation by lapping of substrate, polishing of substrate, and epi-ready of substrate for epitaxial growth. This is the design of the old furnace used in the crystal growth process. We have taken quartz ampule and we do carbon coating in a furnace at 900 degree temperature by cracking of acetone. It is done for avoiding the sticking of high purity material with the inner surface of the quartz ampule. After carbon coating, we are doing degassing of this ampule, and then we weigh the charge cadmium, zinc, and tellurium with zinc 4% stoichiometrically, and placed this charge in this ampule and placed in a quartz and sealed it. After this, we put it in a rocking furnace for 5 days, and after attaining constant temperature, we rock this furnace for mixing the charge. This is the one experiment. We grow this crystal in a quartz ampule and in a graphite crucible, and nowadays we are using PBN crucible. We are growing graphite crucible, but carbon contamination is there. Now PBN crucible is giving very good result for the device purpose. This is the structure of PBN crucible and for growth purpose. Now the growth parameters are temperature gradient, travel rate, post solidification cooling, and furnace diameter is given here. Ampule diameter is 45. Temperature gradient is 3 to 4 degrees centigrade. And after lowering in situ annealing done at 1040 degrees centigrade for 5 days. So, and after that the furnace will be cooled by 10 degree per centigrade per hour to 750 degree, and after that 30 degree centigrade per hour to 300 degrees centigrade. These are the crystals, CZT crystals. This is the requirement of substrate materials. This is the transmission, because this is a backside illuminated, used in backside illuminated device. the transmission requirement is 60%. So our substrate are qualified for this transmission requirement. If substrate is tempered, transmission is tempered when after the uh, annealing, we correct this transmission. This is the zinc distribution. This is the HP density, crystalline quality for the crystalline quality. Some cellular structure is there, and this shows the low angle grain boundaries present in the crystal. In graphite crucible, we minimize the low angle grain boundaries. This shows the different HP density and different type of structure. This is the EPD mapping. This is the X-ray rocking curve. The splitting of X-ray rocking curves, the physical significance of this, the low angle grain boundaries present in the substrate in a one region. This is the perfect single crystalline quality. This is the different size, beam size, and splitting shows that the multiple peaks shows the tilted low angle grain boundaries present in the substrate. These are also analysis. For improvement of the crystalline quality, we are using nowadays PBN crucible. This technology we have transferred to the Central Electronics Limited, Sahibabad, and in two phase we are changing the technology of the diameter of the crystal, and nowadays we have transferred the technology in growth of CZT substrate in PBN crucible. For the temperature requirement, first step, the construction of individual multi-zone furnace. This is the heater module we nowadays we made by Canthal fibrothal module and Canthal wire. And this is the 1 zone and this is the 3 zone furnace, 4 zone prototype furnace we made. For multi-zone furnace, this prototype works. Then we optimize the parameter, and this is the one module of Canthal fibrothal heater module we made. By using 9 such module, we made a multi-zone furnace, 9-zone furnace, and in-house temperature control panel and transformer panel here. So furnace problem is minimized, and this gives the required profile. It is done because we are not getting the Bridgman furnace from US and other countries also because of the sanctions. And this is a strategic material, so people are not giving support or providing the infrastructure for this activity. This is the block diagram of 9-zone furnace, and the temperature profile is there. This is also a temperature profile, constant zone and gradient. This is the final design. There is a low thermal mass of the external bodies. By this design, we transfer the technology of furnace fabrication to the Central Electronics Limited, Sahibabad. This is the output of the crystal grown in these furnace. Just you see the clearly in the twin line is there, and different grain is also visible in the P5 ingot, and twin line is clear in the ingot P4. And the large area grain wafer is shown in the figure. This is the DCRC scanning double crystal rocking curve. This shows splitting at the edges and perfect crystalline quality in the middle of the crystal. Now this is the EPD. This in PBN We minimize the HP density. This is the transmittance. So we provide the solution of the furnace design and fabricated indigenously. We are self-reliant in the field of furnace fabrication and growth of CZT crystals for the focal plane array and, and detector fabrication of IR devices, night vision devices. These are the characterization results. Now the contract signed for Central Electronics Limited Sahiwabad for 5 years and for 300 substrate per annum. And we are the user because SSPL is the semiconductor lab. We have developed the technology and transferred to Central Electronics Limited. And we are getting large number of substrate and growing the epitaxial layer here and making the device, prototype device for missile application, NAG missile, because this substrate is using as a detector in night application in NAG missile. Further, the large size PVN growth is carried out, and Central Electronics Limited production started in Quad Crucible with large diameter also for optimization the parameter, and action is also taken for setting two number of multi-zone furnaces for large dia CZT crystals. Now, this is the other activity, germanium crystal growth activity. Germanium crystals are used in optical materials. So in SSPL, we are using, this is the growth furnace for germanium crystal, and this is the germanium crystal 10-inch. This is the property of germanium crystal for IR optics. Now, other activity is the gallium arsenide crystal growth. So for space application, we are growing gallium arsenide crystals. The growth of undoped semi-insulating gallium arsenide crystals. This is the required pre-growth preparation, gallium arsenide crystal growth and post-growth activity. Fabrication of gallium arsenide wafer from gallium arsenide crystal, because it is a huge crystal. So precious orientation of gallium arsenide wafer along 100 and wafer cutting is required. And the characterization of the gallium arsenide wafer, electrical characterization and structural characterization is done at SSPL. Gallium arsenide is crucial for space and military application. Better operational microwave frequency, greater computing speed and high operating temperature. Application is the gallium arsenide based MMIC set is used as a satellites and missiles. The devices made by SSPL and produced by Gatech Hyderabad is used by ISRO in their space program. We have some commendation certificate from ISRO also. Now the challenges: limited access to availability of knowledge with very few foundries is there. Limitation of sustainable process and manufacturing equipment is there. Low level of maturity of manufacturing as compared to silicon, because silicon foundries are very much available in India. And for gallium arsenide crystal growth, complex growth system is required, induced much larger variety of defects compared to elemental semiconductors such as silicon. Low thermal conductivity of gallium arsenide, which make it sustainable for higher application. Cost of basic research R&D is mostly government sponsored and highly expensive raw material. This is the textbook diagram of the gallium arsenide crystal. This is also. Other technique for gallium arsenide is horizontal beam and vertical method, and vapor pressure controlled Chakrovsky method. So nowadays we are using Chakrovsky method for growth of gallium arsenide crystal. Gallium arsenide activity flow chart is there. Crystal growth, then wafer fabrication and wafer characterization, and we submit this wafer to for other section for device fabrication. This is the Chakrovsky growth furnace for gallium arsenide, and graphite furniture is also used for the inner part of the furnace. This is the gallium molten and arsenic solid, and with B2O3 solid is there, and by rotating, by seeding technique, we grow the gallium arsenide. This is the some other part of the crystal growth furnace. This is the ingot. Grown crystal is there. By orientation of the X-ray goniometer, we in 110 plane, we do cylindrical grinding and flat orientation, flat identification at flat grinding is there. Then wafer cutting, edge rounding and lapping polishing, and then finish wafer for further use. This is the precision orientation gallium arsenide crystals along with wafer cutting. Some other department is doing characterization and give result to us. These are the various characterization results. This is the comparison of American crystal wafer. It is more compatible with our SSPL wafers. Future plan for gallium arsenide growth. We have transferred the crystal growth furnace to the old crystal growth furnace, Chakrovsky furnace, to the Annamalai University, and for further basic R&D research and use for academia. And now we are using crystal growth for a new furnace. These are the parameters, competing materials. So SSPL is doing research in various fields. So as a academia, you are, how you associate with the DRDO. So in DRDO, there are plans from ER and IPR. You can submit proposal to DRDO with your interest field, and by collaboration, you can start the research work. And for student, we are providing training as a academic part, 3 to 4 months, 6 months, and 1 year also. So if anybody wants to contact for training, contact respective director of the lab, and we will support them. And for your, we are nowadays, DRDO is associated with academia. So if faculty members want to take project from DRDO, and they can visit the DRDO website, and they can go to the ER and IPR section, and they can submit proposal for their research with interest related to the defense applications. Then they can collaborate with DRDO. Thank you. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Welcome.
This was
Okay.
very informative and interesting
Thank
lecture
you, sir.
to us.
Thank you, sir. Very informative lecture.
Any question?
हेलो
एनी क्वेरी और
सर।
क्वेश्चन?
सर क्या आप मुझे सुन पा रहे हैं?
हाँ, सुन पा रहा हूँ।
हाँ, मैं सर कानपुर से डॉक्टर अभय सक्सेना। सर मैं
जी
ये जानना चाह रहा हूँ कि क्या डीआरडीओ स्टूडेंट्स के लिए रिसर्च
सर, थोड़ा सा तेज
या
बोलेंगे
कहेंगे
क्योंकि यहाँ बारिश हो रहा है।
अच्छा, क्या स्टूडेंट्स के लिए रिसर्च या उससे रिलेटेड कुछ फैसिलिटीज अवेलेबल कराता
जी,
है?
इसमें दो चीजें हैं। अगर आपका
जी सर।
स्टूडेंट यहाँ पर एक एज ए पार्ट ऑफ एकेडमिक उसमें 3 से 6 मंथ का ट्रेनिंग करना चाहता है, तो हम उसको ट्रेनिंग प्रोवाइड करते हैं। पहला ये हुआ। दूसरा,
जी
अगर आपका कोई पीएचडी स्टूडेंट यहाँ के फैसिलिटी यूज करना चाहता है विथ योर नो ऑब्जेक्शन सर्टिफिकेट एंड कैरेक्टराइजेशन फैसिलिटी यूज करना चाहता है, ग्रोथ फैसिलिटी यूज करना चाहता है, तो आपको हमारे डायरेक्टर को एक पत्र लिखना होगा। वो पत्र कि आप एग्जैक्टली क्या कराना चाहते हैं, तो उसमें परमिशन मिलने के बाद आप यहाँ की फैसिलिटी यूज कर सकते हैं। क्योंकि डीआरडीओ आजकल एकेडमिया में ज़्यादा जोर दे रहा है और एकेडमिया को इन्वॉल्व करके कोलैबोरेटिव रिसर्च के फील्ड में भी कार्य कर रहे हैं। तो ये तो हुई स्टूडेंट की बात। दूसरा हुई कि अगर आप कोई परियोजना लेना चाहते हैं, कुछ लेना चाहते हैं, तो डीआरडीओ में ग्रांट इन इट का फंड होता है। और ईआर
जी
एंड
सर।
आईपीआर एक डायरेक्टेड है, एक्स्ट्रा मोरल रिसर्च एंड इंटेलेक्चुअल प्रॉपर्टी राइट। वहां पे उसका आवेदन करके आप उनसे प्रोजेक्ट लेकर के कोलैबोरेटिव रिसर्च कर सकते
जी थैंक यू। थैंक यू।
Thank you, sir.
Thank you, sir.
हैं। वेलकम। जी।
अगर कोई पार्टिसिपेंट सर से क्वेश्चन पूछना चाह सकता है तो पूछ सकते हैं।
पूछ लीजिए,
जी
अगर फैकल्टी हैं, कोई डाउट हो कि आप हमसे कैसे एसोसिएट हो सकते हैं, बच्चों के लिए कुछ है तो उसके बारे में बताया जा सकता है।
Can you hear me, sir? This is Suman, Dr. Suman. Can you hear me?
यस यस।
Yeah. So I have one query. So I work on oxide single crystal. For example, nickel oxide, manganese oxide, such oxide
जी जी
single.
जी जी।
So I also work on thin films. So I know the techniques for thin film growth. For example, using electron beam evaporators and other techniques, epitaxial thin
यस
film.
यस यस।
But in your opinion, what would be the best method to grow such single crystal? I mean, oxide single crystal. Which,
हेयर हेलो, आई कैन नॉट हियर प्रॉपरली।
so my question is,
यस।
which single crystal growth technique will be suitable for oxide such as nickel oxide, manganese oxide?
You can use a vertical Bridgman method also, or if you write to me, then those who are growing the oxide crystal, we will give your address. They will tell you the exact solution to your this thing problem. Because I
Okay,
am not using growing the gallium arsenide oxide.
okay. I may contact you to, yeah,
Yes.
thank you.
Any other question? Otherwise, I will leave the.
yeah. Uh, Dr. Pandey sir, may I present vote of thanks, sir?
हाँ,
Uh,
बिल्कुल।
uh, uh, Thank you, sir. So, in our today's first session, Mr. Ram Chouksey sir from DRDO has given a nice lecture regarding to the say crystal growth activity and guided us about its importance. So I, on behalf of MM-TTC, RDBB Jabalpur and the whole participants, I thanks Mr. Chouksey sir for his great words, and with the permission, I declare that this lecture is over here. Thank you, sir. Thank you very much, sir.
Thank you. Thank you.
Thanks a lot, sir.
Thank you, sir.
Thank you, sir.
अभी सेकेंड लेक्चर है 12 बजे से।
हाँ सर,
ये इनका है ना, क्या कहते हैं,
राम टिके सर,
राम टेके सर। हाँ,
डॉक्टर राम टिके सर। हो सर।
तो वो तो मेरे ख्याल से 12 बजे आएंगे, है ना।
जी ठीक है सर, ठीक है ना।
अभी कितना बजा है? 11 बजा है।
हाँ हाँ हाँ।